Jyotsarup for the invitation. And I was told by Jyotsarup to talk about my work which I have been doing for the previous years, and also about my journey as a woman in mathematics. So I will start with the technical work, and if the time permits, then I will share the journey also. So I dedicate this talk to the two important people in my life. One is my teacher, Professor IISERM-Maths, whom we lost 2 years ago. People at IISERM-Maths know him very well. And he was my PhD advisor, and he's the one who introduced me to research in mathematics. And then second is my late husband, Pushpinder, whom I lost 7 years ago. And he was a constant support and encouragement for me, and he became my strength. So I'll be talking on my journey on the Wedderburn decomposition in group algebras. So at the end, maybe if the time permits, I will also share how I got interested into the subject. But for the time, I will begin with what I have been doing in the previous years on this topic. So please feel free, since there's a technical talk, feel free to ask any doubt wherever you have in the lecture. So throughout this lecture, all groups are finite. Q is the field of rationals, and QG is you take all Q linear combinations of elements of G, form that set of all Q linear combinations of elements of G, and you add them component wise, and you multiply them using the multiplication in the group G and associativity. So this QG, the set of all formal Q linear combinations of elements of G, becomes an algebra over Q. And Meshige's theorem tells us that this algebra QG, if you take formal Q linear combinations of elements of G, this happens to be a semi-simple ring. So a property of semi-simple rings is that it's written as a direct sum of minimal two-sided ideals, and those minimal two-sided ideals happen to be simple rings. Okay, simple rings, for example, fields, matrices over fields, matrices over division rings. Those are simple rings. Examples of simple rings. So this QG is a direct sum of minimal two-sided ideals, and which are simple rings, and these are uniquely determined by QG, G, and of course the field Q. And this R is also uniquely determined, and these are called simple components of QG. What you know about these simple components AIs, as I just told, that these are simple rings, and they are finite dimensional over its center, because G is a finite group, QG has finite dimension over Q, and therefore AIs will also have finite dimension over its center. And these are central simple algebras, finite dimensional central simple algebras. And one of the properties of finite dimensional central simple algebras is that if you take a simple R module and you take the homomorphisms, R homomorphisms from M to M, then that happens to be a division ring, and this finite dimensional semi-simple algebra becomes a matrix algebra over the opposite ring of D, which is also a division ring. So what I want to say is that finite dimensional central simple algebra is isomorphic to a matrix ring over a division algebra. The size and the division algebras, they are uniquely determined by R. So if you use this, then QG was isomorphic to minimal two-sided ideals. Each minimal two-sided ideal is a matrix algebra over a division ring, and therefore you get this decomposition. This is called Wedderburn-Artin decomposition of the rational group algebra QG, and this determining all these are invariants of this group G. So they just depend upon the group G. It's uniquely determined. The pairs Ni's and Di's are uniquely determined. This R is uniquely determined. And so this problem of determining decomposing QG as a direct sum of matrix algebras over division algebras is a central problem in representation theory, because it leads to the representation of G over Q. And so these are some of the central problems: how to compute the simple components, how to compute the complete Wedderburn decomposition, how to compute what will be R in terms of G. If I give you a group G, can you compute number of simple components? Can you compute the size of the matrices? Can you compute division algebras? Or the square root of the dimension of division algebra over its center is called the Schur index. This is a division algebra. Take its dimension over the center of Di, and that is always a square, and take its square root, that is called the Schur index. And so calculating the Schur indices, all these are central problems in group range representation theory, and they are linked with several other problems in the area. So I will just talk of one terminology which I will be using, Brouwer equivalence. Two central simple. So our aim is to tell as much as you can on this decomposition. If you can completely tell the decomposition, well and good. If you cannot completely tell the decomposition, tell some simple components, some information on the decomposition. So I'll just introduce this terminology, Brouwer equivalence. Two central simple algebras are called Brouwer equivalent if some matrix algebra over A is isomorphic to some matrix algebra over B. For example, if you are given a field K, then K is Brouwer equivalent to 2 cross 2 matrices over K, or any size of matrices over K is Brouwer equivalent to any size of matrices over K. So every finite dimensional semisimple F algebra is Brouwer equivalent to a division algebra over its center F. This is a well-known result in theory of central simple algebras, that every finite dimensional central simple algebra is Brouwer equivalent to a division algebra over with center F. And also every finite dimensional central simple F algebra is Brouwer equivalent to a cross product algebra over F. So our interest is in these central simple algebras. These central simple algebras, this is Brouwer equivalent to Di. This is also Brouwer equivalent to a cross product algebra. So if you can well and good find the division algebra, good. Otherwise try to see cross product algebra which is Brouwer equivalent to this algebra. This will also tell you lots of information on the Schur indices, etc. So what is a cross product algebra? Very briefly, vaguely, I just want to tell you what is a cross product algebra. Group ring, I suppose it is clear to you. If I give you a group G, take formal Q linear combinations of elements of G, multiply them in the most natural way, add them in the most natural way. Now, you just don't take formal, you are given a Galois extension. I am telling you classical cross product, which is slightly easier for me to tell. So, take a Galois extension and take the Galois group of K over. Now this is my group. This is my group G, the Galois group of K over F. Take K linear combinations of elements of G, not elements of G actually. For each group element, you just take a variable, set a variable Zg, and just take K linear combinations of Zg. Zg is one variable associated with every element of the Galois group. Now you can add them in component wise, but how do you multiply 2 Zg and Zh? This is via the twisting. Zg, Zh is Fgh is a factor set on G. It's a mapping from G cross G to this with this sum property. So you can leave the technicalities. What I want to tell you is that they multiply this, like this. If Zg, Zh is this twisting times Zgh, and Zgr is R comes on the left by the action. So there are some technicalities if you have not seen this earlier, but it's a generalization of group rings. And this is called the classical cross product of cyclotomic algebra is that this quaternion algebra is a cyclotomic algebra over Q. This is one example. This you are familiar with, cyclotomic quaternion algebra. Okay. So what Brouwer and Witt proved was that Wedderburn component of semisimple group algebra is Brouwer equivalent to a cyclotomic algebra. So the Wedderburn components which we were seeing are Brouwer equivalent to cyclotomic algebra, but the precise description of the cyclotomic algebra is not available from the proof of Brouwer-Witt theorem. So that is the main objective, to find this cyclotomic algebra which is Brouwer equivalent to the simple components of the group algebra. So I'll describe a method using Schroeder theory which is efficient from the computational perspective, and let me just go through the difficulties in the proof of Brouwer-Witt theorem. So in the proof of Brouwer-Witt theorem, the theorem depends on the p elementary sections of the group.
Sorry, could you go back? What was the Brouwer-Witt theorem?
It says that every Wedderburn component of a semi-simple group algebra is Brouwer equivalent to a cyclotomic algebra. So you are interested in the cyclotomic algebra, which is Brouwer equivalent to simple components of QG. So the difficulty in the proof of Brouwer-Witt theorem was it depended on the p elementary sections of the group, and there was no way to determine those p elementary sections. So what these people, Oliveira, Del Rio and Simon, did in 2004, they replaced p elementary sections with so-called strongly monomial characters of subgroups, and then they reproved Brouwer-Witt theorem using the strongly monomial characters of subgroups. But again, there was no theoretical method to determine the p elementary strongly monomial characters of subgroups. Also, they used the help of gap package. To given a group G, they use the help of gap package to determine the strongly monomial characters of subgroups to tell the corresponding cyclotomic algebra which was occurring. And so this is what me and Jyoti have been doing lately, and before that Gurleen, we started with this work, and before that Sugandha. So it's a decade-long story that I have been interested in this subject. So let me start with a simple example where the things are easy for you to see, but as soon as you go from abelian to non-abelian, the character theory comes into play. So if you take so this is fine. Take a cyclic group of order 7, and this is your Q. Now what is this QG? QG is, take the polynomials over Q and take quotient with x to the 7 minus 1, it becomes this group algebra of a cyclic group of order 7. Now, what you want to do, you want to break this algebra into direct sum of simple rings. But now since it's all abelian, those simple rings will be just fields. So the breaking is that you break x to the 7 minus 1 into irreducible polynomials, and then this is the breakage, and then this is Q, and this is Q zeta 7. If you have done some field theory course, then you can recognize that this is just Q zeta 7, and so this decomposition is the direct sum of two fields, and this is the Wedderburn decomposition. Things are pretty decent when you have, say, cyclic group exactly the same way. If you have a cyclic group of order n, then you decompose x to the n minus 1 into irreducible polynomials, which you know cyclotomic polynomials, and then this is the breaking. Moving from cyclic to abelian, Perlis and Walker in 1950 gave this decomposition that if you have an abelian group of order n, then this decomposition is precisely can be given from the cyclic subgroups of G. If you have the knowledge of cyclic subgroups of G, then you can write down this decomposition. Okay, so this is precisely how many Q zeta d. Zeta d is a primitive dth root of unity. You adjoin to Q, and it is the number of cyclic subgroups of G of order d. So very nice theorem. For example, if you have G C2 cross C4, determine the number of cyclic subgroups of each order, and then use Paulus-Walker, very beautiful theorem that it gives you decomposition. Now moving from abelian to non-abelian groups. So the theory of abelian groups is very decent, very nice, neat and clean. But when we move from abelian to non-abelian groups, it depends on the characters of the group. So let me give you some terminology. I cannot do anything without this terminology, but if those students who know representation theory, they already are aware of this terminology anyway. So if you have an irreducible character of G, complex irreducible character of G, okay, then and Q chi is that to Q adjoin all the character values, then you form this group ring element. You form this group ring element. This is an element of CG and this is a primitive central idempotent of CG. Okay. It will generate a two-sided ideal of CG, which is a simple component of CG. But if you add simple components of CG corresponding to the irreducible characters, which are Galois conjugate, so if you take sigma in the Galois group of Q chi over Q and you add the primitive central idempotence of CG, then you get primitive central idempotence of QG. Primitive central idempotence of QG, if you take two-sided ideal, if you take ideal generated by this, it's a central element. If you just take ideal generated by this, then it's a minimal two-sided ideal of QG and therefore it's a simple component of QG. Well, very good. You know idempotent, so you just take all characters of G, take all complex irreducible characters of G, separate them in the Galois conjugacy classes and then compute these guys and they will give you all primitive central idempotents of QG. Take ideals generated by them, they will give all the minimal two-sided ideals, so-called simple components of QG. But where is the decomposition? Where are the matrices? Where are the division algebras? Where are the cyclotomic algebras? All that theory needs to be told from the character chi. So that is the problem. So the cyclotomic algebra, which is Brouwer equivalent to the ideal generated by this primitive central idempotent of QG, and what is the Schur index of this primitive this two-sided ideal of QG, and so that is what the study demands. And so I will just introduce you to monomial characters, which is monomial groups are quite a rich class of solvable groups, and there has been a lot of work in this direction. A character of G is called monomial if it is induced from a linear character of a subgroup. See, linear characters are easy to see. Linear character of a group meaning you have a homomorphism from G to non-zero elements of a group. That is what linear character of G is. So complex linear character of G means a homomorphism from G to non-zero complex numbers. But you can also have linear characters of subgroups of G and you induce them to G. If after induction they happen to be irreducible characters, then those are monomial irreducible characters. Otherwise you can also talk of a monomial character which is induced from a linear character of a subgroup. A monomial group is the one where all irreducible characters are monomial. Each irreducible character can be lifted from a linear character of a subgroup. So some examples of monomial groups are nilpotent groups, metabelian groups, supersolvable groups, abelian by supersolvable groups. Nice examples of monomial groups. And the beauty of monomial groups that it is rich is that they prove that every solvable group can be embedded inside a monomial group. So it's quite a decent class. Remember, subgroup of a monomial group is not necessarily monomial. Otherwise, all solvable will turn out to be monomial. Okay. So Schoda's theorem tells you, first of all, if you want to understand monomial characters and you want to understand simple components corresponding to monomial irreducible characters, then you want to understand from where they are coming. Suppose you have a monomial irreducible character, It means that it is induced from a linear character of a subgroup H, and linear character on H meaning that I am interested in the kernel K, kernel of that character also. What is the kernel of that character? So if lambda is a linear character on H with kernel K, then the pair H comma K has these two properties. The character will be irreducible if and only if H and K have these two properties. You can forget the technical details if you are new to this representations or monomial characters or something, but you can just think that Shoda gave a criteria, necessary and sufficient condition that when is an induced character irreducible, induced from a linear character of a subgroup, irreducible. So what should be the conditions on H and K, so that if I take a linear character on H with kernel K, induce it to G, it is irreducible. So such pairs of subgroups H comma K which have the property that if you take a linear character on H with kernel K, the induced character is irreducible. So those are called Shoda pairs of G. So Oliveira, Delry and Simon gave them the name Shoda pair of G. So HK is a Shoda pair if and only if lambda induced to G is irreducible, where lambda is a linear character on H with kernel K. So whenever I want,
excuse me, I could not get why they are called Shoda pairs. Shoda is a mathematician.
Shoda is a mathematician, yes. So these are the necessary and sufficient condition given by Shoda that when is a character, linear character induced to G irreducible.
So, sorry, this is for every lambda or it's for some lambda?
Linear lambda.
For every linear lambda?
For every linear lambda. For every linear lambda, so if H and K satisfy these two properties, then the induced character is irreducible.
Okay, so for every lambda, for every multiplicative character. Linear is what you are calling this.
1 degree character.
Homomorphism to B star.
Yeah.
C star.
Yeah. So if you take, so basically if I take a Shoda pair of a group and take a linear character on H with kernel K, 1 degree character, then I have a monomial irreducible character. Then therefore I can compute this primitive central idempotent. I told you when I have an irreducible complex character, I can compute a primitive central idempotent. Therefore you can generate an ideal with that. So what is the cyclotomic algebra Brouwer equivalent to this simple component of QG? And so that is what the story is. And Oliveira, Delry and Simon called, okay, so they strengthened the condition of a Shoda pair to initiate on this topic, and I will just relax the condition later on. So a Shoda pair is called a strong Shoda pair. They are just adding one more constraint so that something can be said. We will relax the constraint later on. So you just add a Shoda pair is called a strong Shoda pair if some more constraints are added on this group. You get a nice pairs of nice groups with this property too. I will tell you the groups, but you just assume that some more constraints are given on a Shoda pair, and this is what is called a strong Shoda pair. You are making it strong, imposing more conditions. And a finite group whose all complex irreducible characters are induced from strong Shoda pairs, they are called strongly monomial groups. And examples of strongly monomial groups, they proved in their paper that abelian bi-supersolvable groups are strongly monomial. Here, irreducible characters are monomial, and they come not only from Shoda pairs, but they come from strong Shoda pairs. Shoda pairs with some special properties which they demanded to give the cyclotomic algebra Brouwer equivalent to the simple component. So this is a beautiful theorem which they proved in 2004, that if you take a strong Shoda pair, then this simple component is isomorphic to this matrix algebra over this classical cyclotomic algebra, I am just skipping the technical details, but this is precisely alternative proof of Brouwer-Witt theorem, but very precise proof from the group G that you can give such a thing. You can tell such a thing. So when I looked at this paper for the first time, I remember for several months, maybe for 6 months, I could not understand this paper. What was actually contained in this paper? Why are they doing all this story? But eventually, after reading it again and again, see, paper is never clear to you once you read it 1 or 2 times. To digest a paper, you have to see the theorem 10 times or maybe 20 times. Only then you can digest that result. See the beauty, see why they are doing all that stuff. So the problem is, okay, they have told if you have a strong Schoda pair, then this is the matrix algebra over this cyclotomic algebra. But the question is how to find Schoda pairs. There are technical difficulties in finding. If I give you a group, how will you find Schoda pairs? How will you find its strong Schoda pairs? How will you find 2 strong Schoda pairs which are giving different simple components, and so on. So those were the kind of things which came up. And so how to determine Schoda pairs? How to determine Schoda pairs which give distinct primitive central idempotent, so-called irredundant set of strong Schoda pairs. And what to do if you have a Schoda pair but not a strong Schoda pair? So, which means that I am asking for a generalization of this theorem when you have a Schoda pair but not a strong Schoda pair. So all these theorems came up when we were reading that paper. And the first time Professor Kulkarni came to Punjab University in 2008 for an ATM school. He was there for the entire month there. So I was studying this paper at that time. So I continued discussions with him and also with Professor Pasi. And after working for 2 years or so, 2-3 years, it took more time to publish, but we proved in 2011 or something, we could prove this result that if you have metabelian groups, metabelian meaning abelian extended with abelian. If you have metabelian groups, then we can tell precise algorithm to compute Schoda pairs, of course strong Schoda pairs, and all the machinery which was involved in the Wedderburn decomposition. So at that time, if you give us metabelian groups, we were able to do the computations of Schoda pairs, strong Schoda pairs and all that. So the story started in this paper. So after that, in this work with Sugandha joined for PhD, and in this work with Sugandha, so what we saw that the property of metabelian groups was that each irreducible character is not only monomial, it is coming from a linear character of a subgroup, but that subgroup from where it was coming was a normal subgroup. So
PCI stands for principal
primitive central idempotent. Primitive central idempotent. Yeah. So that was one observation we did in metabelian groups, that irreducible characters are induced from normal subgroups. So we said, let's look at those Schoda pairs, those strong Schoda pairs, such that H is normal in G. We called it an extremely strong Schoda pair. So we just added one more constraint. Already there were constraints, but we added one more constraint and wanted to see what comes up. So we added one more constraint, that H is normal in G, called it an extremely strong Schoda pair, and groups where all irreducible characters come from extremely strong Schoda pairs, we called extremely strongly monomial groups. But that time it was looking like we were adding too many adjectives to it, but now it has been of great help. I will tell you how. So we gave a complete algorithm. I will not go into the technical details. So what we did, that by adding that constraint, we were able